Good morning, good afternoon, good evening, everyone, and thank you all for being here today. My name is Charlie Collius, and I am the Product Marketing Manager for the Equipment Group here at AFL, and today we have a very informative Splicer presentation for you. Megha Garalapati is AFL's Splicer Product Manager, and Craig Henderson is a Senior Applications Engineer at AFL, and they will present Mastering 16 Fiber Splicing for Hyperscale Data Centers. So before we kick this off, before we begin here today, I just want to go over some housekeeping tips. If you have a question at any time during the presentation today, please submit it in the questions box in the control panel on your screen. Just click the question mark icon in the upper right and send it to us there. We will answer them at the end of the presentation. And then today's slide deck is available to download by clicking the handouts icon in the right side, and there's a PDF for you there to follow along with or reference afterwards if you like. All attendees here are in listen-only mode to reduce the background noise during the webinar. And today's webinar is indeed being recorded and should last about 45 minutes. And a link with where to view the recording will be sent out in the next couple of days. So with that, we've got a lot to get through. I want to ask Craig Henderson to start today's presentation. Craig.
Thank you, Charlie. I appreciate it. Welcome, everyone. This should be a fairly informative session. We're going to start out with the agenda. And also, I want to ask Megha to say hello right quick, just to make sure you have his voice versus mine.
Hey, everyone. Good afternoon and morning, whoever is joining from around the globe. Thanks for joining this webinar. There is a lot to cover, and let's begin that.
Okay, we're going to start out the agenda. Of course, this is mass fusion splicing in the hyperscale environment. And the agenda will be as follows. I'm going to kind of discuss the market context, the size and scope of these hyperscale centers, which are quite massive. We're also going to cover the splicing environment as far as what you can expect in a hyperscale build where you're actually doing the work on site. Overview of the ribbon splicing challenges in this environment. We wish it was a clean room environment, but as you can see, it's a massive building with lots of construction happening. We'll move on to tools overview. We'll be covering the 90R, the fixed V groove mass fusion splicer, the hot jacket stripper, and of course the cleaving device that is critical to this operation. We're going to touch on the fiber types and standards. We're going to touch on the physical makeup of the ribbons you may come across in the industry and what you can expect. And then what we think is critical to doing quality splicing on a repetitive basis, which is a lot of stuff revolving around the processes and procedures before you ever make that fiber optic cleave. And then we'll end with a fairly quick question and answer session. We'll give you about maybe 15 minutes if we have it, and go from there. As Charlie mentioned, please get your questions in, and Megha will be reviewing those. We will probably take the most of them at the end, but that being said, we may hit some on the slide that we're currently on as well. Let's start with the hyperscale industry and what we're dealing with. Today, we have approximately 1,100 hyperscale data centers in existence globally. This has doubled in size from just 5 years ago. So there's massive influx of materials. Matter of fact, if you look at the fiber miles allocations, the majority of this stuff is going into this hyperscale build. Just one hypercenter will have hundreds of thousands to millions of connections on that. When we say connections, we're not only talking about the mechanical connectors like a Sam Charlie, LC connector, MPOs. We're also talking about the physical splice itself. That being said, in these data center builds, fusion splicing is going to represent 70 to 85% of total connections. This is through the inter-building and intra-campus connectivity that will occur from one building to the next. Year-over-year growth. Here's the projections over the next 5 years. You can see we're right now, 2025, we're sitting at 6.2 billion connectors. That's with a B. It's going to rapidly increase to over 9 billion by 2028. So no end in sight from the standpoint of the volume of splicing is going to take place. Tremendous amount of work to be done. Of course, this is due to rapid expansion in the AI cloud services, the edge computing, and this was where all the, again, the capacity fiber allocation on the world demand, quite a majority of that fiber is going into that hyperscale build environment. Wanted to start out by touching on real world conditions and the relative size of particles. I'm responsible also providing a lot of hands-on training for our mass fusion technology and outside plant environment. And just to give you scope of size here, wanted to talk about some of these elements here. Your common dust particle, that's going to be extremely small in the 8-9 micron range. And you can see on this line, I'm going to turn on my laser pointer and highlight something for you right quick. This little line here represent the point at which the human eye can actually see a particle of that size. And I always like to use the analogy of a particle floating in space, going through like a light ray passing through the window. We've all seen this particle floating around in the air. That particle is, if you can see it with the naked eye, approximately 15 microns. That's 1.5 the diameter of the size of a single mode fiber optic cable. In real world hyperscale builds, when you first start these things out, they're massive facilities. They have a lot of earth moving vehicles in, moving material, lots of concrete being made, lots of concrete being cut. There is quite a bit of issues with the systems. We're not in the clean room environment, major amounts of dust, and of course you're dealing with outside plant environments at that point because they do not have temperature control. The temporary infrastructure, this forces you to bring possibly a generator to a location to make a splice. You're in an unstable situation where you've got makeshift setups, tents, and trailers. Construction interference. Of course, we've got noise, vibration, airborne debris. This is just real world conditions you're having to deal with. And of course, with this high demand on cleanliness, you are in a situation where you're going to be frequently cleaning the tools. This is essential to prevent contamination and ensure precision. And this is something that has to be done right 100% of the time, and it's no exceptions to the rule. And this is kind of how does this situation deal as far as the fiber you're dealing with. Here's what a fiber compares with. The illustrations you see here on the left-hand side is 150 microns. This is your average human hair. You get into lint particles, 25 microns, heavy dust, lint, fertilizer, pollen, 10 microns. If I show another view to you, this is your structure of a standard 200 coated or 250 micron coated fiber, which is your typical UV acrylic that surrounds a 125 micron cladding. The illustration that's popping up, this little section is the fiber 125 micron cladding as it compares to the fiber optic cleaver, such as a CT50 fiber optic cleaver. You'll see the edge of the blade as it compares to the relative size of the fiber. And keep in mind that that fiber that you see sitting on top of that blade, that is the 125 micron cladding, and we're still are trying to align that 9 micron core in that fiber. And that's what's carrying the signal that you're trying to minimize loss with. We're going to review the tools right quick. First thing is the mass fusion splicer. This is a critical element of the system that you see in front of you is the Fujikura 90R. These systems have been in place since 1990 in the telecommunication industry, and we've learned quite a bit on correct quality splicing using these systems. They are fixed V-groove, meaning the V-grooves themselves are stationary. So you have to be very much on your P's and Q's from the standpoint of controlling contamination and fiber prep work leading up to the actual splice. Reliable, high-duty systems. They can be used with battery packs. They can be used with generators with no issues. Ribbon splicing tool. This is the mechanism that you would remove the UV acrylic off the ribbon array. And when I say ribbon array, that can be what we call encapsulated ribbon, or that can be rollable ribbon, or that can be individual fibers that have been ribbonized into a ribbon array. The hot jacket stripper will apply heat to the section that needs to be removed. It helps loosen that primary jacket, which is the UV acrylic, off the cladding of the fiber, and to help you remove that material as easily as possible. If not, without heat, you would experience a lot of fiber breaks, and you have a real difficult time getting through this step. The cleaver, the fiber optic cleaver, in my opinion, is probably one of the most misunderstood tools in the industry. I tell folks all the time, this is 1/10 the cost of a fusion splicer, but it is 50% of the splicing process. So we're going to pay a lot of attention to the cleaver, and I think this tool, if used properly and understood, will greatly magnify the success when you're outside in that real world hyperscale build location. We will also discuss accessories a little bit. What you see when I say accessories, we would be talking about the fiber holders themselves. There are a lot of different flavors of fiber holders that we can bring to this mass fusion splicer. The fiber holder that you see here is a F870-12PC. PC stands for pitch conversion. So on the back side of this fiber, maybe 200 micron coming into the back of the fiber coating diameter, and we will actually spread those fibers out to go in this V-groove. The V-groove that is installed with these PCs would be a 250 micron V-groove. As you move into the hyperscale world, you're going to see a lot of 200 micron coated fiber. It only stands to reason that you would set up the system to place another accessory in place of this 250 micron V groove, and that would be the 200 micron V groove, so that it would match the fiber that you're splicing. And we're going to talk quite a bit about accessories moving forward. Cleaning wipes. What you see in front of you is the AFL lint-free variation of cleaning wipe. The thing you have to remember here is you want it to be lint-free. Again, you're dealing with small cores here, so you don't want a wipe that possibly could be shedding on you. Cleaning fluid. The cleaning fluid that you see here is AFL's variation of cleaning fluid. Excellent material. It evaporates extremely fast, and it leaves no residue on that cladding of that fiber. This is also the same material you would use to clean the V-grooves, the V-groove chip clamps, and the fiber itself. And then we will finish with an inspection kit. This device, when typically in the industry, when you think inspection, you're thinking about some type of magnifier that you would look at the end face of a connector to ensure the cleanliness of the connector. In this particular case, this tool was developed as a result of when we introduced the mass fusion splicers in 1990. We were constantly writing on the service request clean V grooves, and we got a lot of calls with technicians saying, I know I cleaned those V grooves. The problem with this is they really didn't have the ability to see what we were seeing, because we were using a stereo microscope. We were magnifying that fiber approximately 50 times, and looking at those V grooves blown up about 30 times with that stereo microscope. So the inspection kit has a little jeweler's lube and also a little white pin light to allow us to, the operator in the field, to magnify and inspect those V grooves, which is a critical part of that operation. Talk a little bit about transport. This is a kind of a new development for us. We have these cleats that we can put on the bottom of our splice case. And as you can see on the bottom picture, that splice case with those cleats on it will mount onto the industry available Milwaukee pack-out system. This will anchor that into place. You don't have to worry about it rolling off the side. You can roll it across the facility. Also on the transport side, we have a new mobile splicing workstation. It is actually a work table, but on the bottom, it has casters, so we can use it as a dolly to move material through a warehouse if you'd like to do that. That is the mobile splicing workstation as it's elevated. You can see here it's got telescoping legs. The legs move out towards the corners, very stable. You can put approximately 400 pounds on the top of this mobile splicing workstation. But again, it's about portability. And then, of course, you do want to use, in this environment in the hyperscale world, a lighting tree or something you can bring to make sure that you're able to see these small products. As we move forward, some key questions. This in the industry is, what's the International Telecommunication Union specification for fiber? We call this ITU. And why does that matter? First of all, it determines the core size, mode field diameter, and bend radius. So if you call the facility and talk with me or another engineer, we're going to ask you, what is the ITU spec of this fiber? Hopefully it's a homogeneous where you're splicing the same ITU spec to the same fiber, but in some cases that's not going to happen. We are, again, in real world environments, and we don't always get the fiber we want to use and make that decision ourselves. This impacts the splice loss and compatibility between fibers. I can tell you, if we're splicing an ITU G.652 to G.657, we're not going to get that 0 dB splice just because of the characteristics of the individual fibers. Guide splicer programs, they may be a case where you would have to have a specialized program for the fiber type that you're working with. Conceptually, that's true, but in reality, 99% of the material that you'll be coming across in the hyperscale world will be homogeneous, and you can use a standard single mode program. So very little difference in arc temperature, the arc power, the arc time, the prefuse. Those mechanisms probably will not change for you in real world environments. Common ITU specifications. The first one is the G.652. The revision we have now is G.652.D. That's what's being manufactured today. This is standard single mode fiber in the industry back in 1985, 1990. It was just known as single mode fiber, SMF. Most common in legacy networks. So if you're bringing this hyperscale into a local community and you've got to bring fiber to it, you may be making this G.652 from the legacy fiber into the new system. G.654E, this is large mode field diameter fiber. In the industry, you may use the term LEAF, large effective area fiber. It's typically used in the long haul networks. Very common in the long haul systems of AT&T, Verizon. Some of these terrestrial systems in the utility world will use a large effective area fiber. And the net effect is specifying that 1550 nanometer C-band channel and carrying that signal as far as possible without the need for a repeater. Good news is it's rarely seen in the hyperscale builds. You won't see this fiber too much. Then you get into the ITU G.657 A1s and A2s. This is the bend insensitive type fiber. We call it BIF. And this fiber is utilized with high fiber count systems, the 3456, and larger cable builds would use this G.657 fiber. And that really means it's bend insensitive, so you're able to pack more fiber into a smaller cross-sectional footing, so to speak, and you can bind that a little bit tighter, and you can get higher fiber counts in your cable as a result of using this bend insensitive fiber. It's frequently used in a hyperscale build. You will see this type fiber on par more than anything else. There is some good news with this. It usually also carries the ITU G.652D compliance. So splicing it to the legacy fiber, you don't see too many issues. The fiber on the right, the illustration that you see here, is a G.652 on the left-hand side. And again, this is the X image left side. This is a Y image left side. And we're going to be splicing this to a G.657A1. I'm just going to quickly press enter, and we're going to go through this splice process. By the way, this is a splice made with our active profile alignment system, the 90S Fusion Splicer. So that is the splice being made, and you'll notice that there's a slight line between the splice on both the X field of view and the Y field of view. This is not unusual. So I'm going to go in and I'm going to turn my laser pointer off, and I'm going to pull back this video, and I want to show a couple of things. First thing I want to illustrate is this little area here. If I point it out with the laser pointer, you'll see this little bright spot. This is what we would call a hot spot. This is fairly normal in this industry. It's a fairly small piece of glass that may have chipped off, or a piece of small debris that may be on the outside circumference of that fiber, and you'll see this flash up. What I want to illustrate here is a word of caution. If there is a very large hot spot and you see it both on the X axis and the Y axis, that means it's getting into that core area, and it could be subject to a really poor quality splice at that point, and certainly would need more attention as you go to measure it with your light source and power meter, or possibly an OTDR. And now I'm going to pan back over and just pull up and bring up the illustration of the arc. Something you will notice, the G.652 fiber on the left is burning a little bit brighter than the G.657 on the right. Fairly common that you'll see this in the industry, and it can be two G.657 fibers that has this type of phenomena. This is a byproduct of the energy going into that fiber and the luminance coming off the fiber. This also tells you that when you go to shoot it with the OTDR, that you're going to have more than likely a backscatter coefficient difference between those two fibers. This type of splice is one you can expect to see a loss in one direction and the gainer in the other as a result of either a mode field mismatch where the chords are slightly different, or you have a different backscatter coefficient in the glass itself. So when you see this, don't be surprised if you're using an OTDR in a unidirectional manner, one direction, that you may see a gainer or a tremendous loss. That being said, the chart on the bottom is actually showing the loss distribution for this particular fiber, which is a .02 minimum up to a .07 max. So that's somewhat expected. You're not going to get the 0-0 splice with this particular combination. Let's move into another key question. What are the physical characteristics of the rollable ribbon? Bonding methods. This really goes back to how is those fibers bonded together side by side. The first bonding method, and the one that has been used since 1990, is what we call an encapsulated ribbon or rigid ribbon. You can see that the UV acrylic on the fibers themselves individually has been overcoated with a second compound, which is usually a UV style acrylic that's been cured. And that will encapsulate not only the edge of the ribbon, but it also will ride over the top of the ribbon. With a bonding method encapsulated, we also have an encapsulated with intermittent slits, and we'll talk about that in just a moment. Edge bonding is what has been kind of taking place with these new rollable ribbons. The edge bonding, as you see, is lying between the fibers. There is no bond material coming up on the top or the bottom sections of that UV primary acrylic of a bare fiber. And you can see in this case on the second level would be 200 micron fiber with a 250 micron pitch. And we'll get into pitch in just a little bit and discuss that. Overlay bonding. This is a issue where this illustration doesn't do an overlay bonding quite right. As you can see, the bond material is laying on the top side of the fiber. In reality, if you look at this under the microscope, that overlay bonding is kind of a UV material that's been bonded in a sine wave pattern across those 12 fibers and oscillates from top to bottom as it moves longitudinally down the line. And that would be one of the bonding methods used. Bonding patterns. Encapsulated ribbon, as you can see on the bottom, this is what you would see with the traditional rigid ribbon. On a scale of 1 to 10, spliceability, this is probably going to be a 10. Going to be very easy to splice, strip, clean, cleave. It holds its parallelness of the fiber very well during that process. Encapsulated with intermittent slits. This is where the manufacturers would take a encapsulated ribbon, then they would cut small slits in every other fiber. I call this 2x2 bonding. And as you can see, this layout of this ribbon, after they cut those slits, you can physically separate those fibers in 2 fiber bundles longitudinally. I like to bring up the first rollable ribbon in the industry. I call it, it's Fujikura SWR, spiderweb ribbon. I can tell you that Fujikura's spiderweb ribbon is a rollable ribbon, but other manufacturers out there are not spiderweb ribbons. And the bonding pattern is unique. If you can look at, starting at the blue-orange, it is sequential. As it bonds, it moves down, moves down, moves down. This lends itself to the fusion splicer, the fiber holders, making a almost as good as rigid ribbon splice. On a scale of 1 to 10, this is probably in the 8, 9 range. I find it to be easy, fairly easy to work with, but it's not nearly as easy as the rigid ribbon that you're used to in the legacy fibers. Rollable ribbon. This is the pattern that you typically see. I call it a 2x2 bond where 2 fibers are glued together, but they are edge bonded, very easy to use. On the scale, I would say these are, between 7 and 9, depending on the manufacturer. The overlay ribbon, this is where you've got that edge bonding, that sine wave running on top of the fiber. And again, this is a continuous run of adhesive. It's not little tacks as you see illustrated here. It's actually a continuous line of adhesive over the top of the fiber. This fiber, it splices pretty good as long as you don't try to pitch convert it. Going from 200 to 250, if you keep it at 200, use the 200 micron fiber holders, 200 micron V grooves, you should have a fairly good success. The only negative to this is since that material is riding up on top of the ribbon, it has a tendency, you don't want to lay the bonding on the bottom of your fiber holder, meaning you don't want that flipped over 180 degrees and clamp with the bonding laying in the channel the surface of the fiber holder. Why this matters, practical effects on splicing, right? First of all, you've got your fiber holders, and the fiber holders are going to be associated with pitch. You got a 200 micron ribbon, you set in a 200 micron fiber holder, you're going to have a 200 micron pitch. The same thing goes for 250, but with 250, you have the option of doing a 200 micron pitch ribbon or a 200 micron pitch ribbon that you have pitch converted to 250. Either way, it's going to be core center to core center is going to be 250 microns. And then, of course, you would select the correct fiber holder, either a 200 micron V groove with a 200 micron bottom of V groove to bottom V groove of being 200 micron pitch, or the same thing for 250. And this is just a relationship, right? So when we go to put 200 micron into 200 micron V groove, you will have good physical characteristics of those fibers aligning with each other. And the same goes for 250. Hope that makes sense. This is also important for your strippers. When you go to use a stripper, the old legacy of what an encapsulated ribbon, you're probably going to use a heat pattern of around 2. With the rollable ribbons out there, you're going to use a higher heat setting of around 4. Prep techniques, every one of these ribbons in the industry will have little bitty nuances that you should know to give you the best possible chance of making a quality splice. What is pitch? This illustration is pretty cool. It essentially defines how far apart the fibers are from each other. It's a relationship between the pitch and the coating diameter. So with these V grooves, the left V groove is 250 microns, the right V groove is 200. Matter of fact, we do have V grooves available in 12 fiber 250, 16 fiber 250, and the same for 200 micron pitch. We have 200 micron 12 fiber and 200 micron 16 fiber V grooves. From peak to peak, as you can see, 250, 200, 250 micron coated fiber will lay into those fibers. You'll notice that the coating edges are touching each other between the orange and blue fiber. And the same goes for 200 micron coated fiber. You'll notice the coating is touching. In both cases, the fiber is 125 micron cladding. That is the material that is sitting into the V groove. 250 pitch, 200 pitch, no problems with that combination. But if you go and take 200 and put it in 250, as long as the pitch is correct, you have no problems putting a 200 micron fiber into a 250 micron V groove. This is the point of pitch conversion. But if you take a 250 and you roll it into the 200 micron, you actually have a physical contact issue, and of course, this will not work at all. You have to use 200 micron with the 200 micron V grooves, or maybe 190 or 180 coated fiber. I've heard that as spec sheets before, and that certainly would be acceptable. Let's talk a little bit about some of the things I think are critical to being successful in a hyperscale splicing environment. Debris and cleaning. First of all, V grooves are absolutely paramount that they be clean. This is an illustration of why we developed the V groove cleaning kit. We've had customers that were trying to tell us that was clean V grooves. With the naked eye, you would make that assumption, but as soon as you put it under a stereo microscope, this is what you get. It's what can be seen. The whole purpose of a fixed V groove system and how it aligns is an illustration on the right-hand side. You see the sidewalls of the V groove, you see the cladding edge. As long as those two elements are very clean, you will get a very good contact point on the sidewalls of the V groove. And of course, over the top is this V groove chip clamp. It pushes pressure right on the top of that fiber. And I call this 3-point alignment. with a fixed V groove system. It's absolutely critical that you do this. And if you do have debris present, you're just going to have axle offset readings, a lot of problems associated with the physical alignment of those fibers in those V grooves. This is what a clean V groove would look like. And then if you don't have a clean V groove, this is what you experienced in your fusion splicer. You will get these higher offsets. You can see the machine has triggered an alarm. It's called large fiber offset. 5.2 microns on fiber number 4 and 6.7 microns in groove number 10. It's absolutely must that those V grooves be clean, and that's critical. That's half the process that has to be done. The second one is choosing the correct accessories. Use a magnifier and light to inspect the V grooves. I mentioned this earlier. One note of caution, the electrodes themselves, very quickly, over a duration of about 30 arcs, we will get a buildup of silica oxide. It appears as a white chalky substance on the electrodes, and what that is vaporized glass that has been pulled to the cathode and anode, the electrodes, and it will build up and it creates a little bit of an oscillation, and it happens very quickly. So what we recommend when you replace the electrodes is do an arc stabilization, which you would build up that silica oxide, and then from there you would periodically clean your V grooves and keep your Q-tip away from that electrode. If you happen to hit the electrode with a Q-tip, you can knock that silica oxide off. What it would do would create a path of least resistance. It's a bare metal location, and that arc would jump not from the tips to tips, but it could possibly banana arc and move over to the far left or far right and not arc properly as a result of that silica oxide being knocked off by the cleaning agents or the cleaning swabs. Again, coming back to the cleaning kit, a necessary product. I don't really need it for single fiber splicing, but for mass fusion, I go through a lot of Q-tips kind of on a regular basis. Pre-cleave conditions. We'll touch on this right quick. We've got a few more minutes. First thing, when I go through and train a technician, at the point when they finish cleaning and they take that fiber that's been loaded in that fiber holder and they move it to the cleaver, I'll say, time out. Let me take a look at it. If it doesn't look what you see here, you're going to have problems. All 12 fibers need to be parallel. They don't need to be touching. They stay in balance. And the cleaver requires balance to produce quality cleaves. I'll move on to another illustration. This is just the end view. You can see those 12 fibers perfectly spaced. I would have no problem setting it in my fiber optic cleaver and moving forward. If you do that properly, once you cleave it and you go to load it into your machine, it's going to lock into position very easily for you. You've got the correct pitch spacing. You got good clean V grooves. You got good clean fiber. Everything's parallel. You made a quality cleave. And at this point, it becomes easy. If you do those things correctly on the front end, the splicing portion of it is no problem for you. Again, this is avoid entanglements. You'll notice here a cleaver is about balance. A needs to equal B. And you'll see on the left-hand side, you got fibers touching each other. You may have some entanglements where one fiber is laying on the top of the other. Big negative here. If I saw this, I would not push this forward and try to cleave it. You're just asking for trouble at that point in time. Avoid separations, the same thing. If you got a lot of separations, when it cleaves that fiber down the center line, what you're going to find when those fibers fall into the ribbon array where fibers number 1 and 2 and 11 and 12 move towards the center, they're going to be the longer of the 12 fibers that you cleave because there's a greater distance from center line of the blade to the end of the fiber. It looks subtle, but it can cause problems for you. And finally, parallel issues. You'll notice here the pad spacing. This space, there's a little bit more room on the pad on the left versus the pad on the right. The ribbon array is actually moving upward. This is a big negative too. Just something you just don't want to try to push through your cleaver, or it's going to create a lot of problems. You got to solve it on the front end. And proper stripping, the only reason I bring this up, if you happen to have a slip of the coating in your fiber holder, if there's any coating protruding up past this point, if you put this into the cleaver, what's going to happen is that coating is going to be on top of that cleaver pad. Cleaver likes balance. You're in balance. You're going to get poor quality cleaving, and you may even get that coating in the V groove, which you got 250 micron coating, where a 125 micron cladding fiber is supposed to be. Obviously, it's not going to work. Okay, we're going to kick it off for a question and answer session. Mega, you want to shoot out some questions for me?
Yes. Awesome. This was wonderful. And I just want to reiterate again that we do have a question column on your right in the tab. So anyone have any questions, please send your questions in there. So the first one, what we have here is how do we use our current 90R to do a 16 fibers splicing?
Pretty simple question. The first thing you have to ask yourself when you say 16 fiber is the ITU spec, what type of fiber are we dealing with? And secondly, what's the physical characteristics of that ribbon? In the hyperscale world today, the majority of the splice being made is 200 micron coated fiber. I would suggest using what we call our red label fiber holders and V grooves, 200 micron 16 fiber V grooves, and 200 micron 16 fiber holders. At that point, it's just a standard splicing process that's from A to Z, so it should be no problem for you.
So do we have a recipe for that?
The recipe is controlled by the machine's quality control. When you do an arc calibration, this will automatically tune that splicer for doing 12 fibers, 1 fiber, 16 fiber. So you just have to do periodic arc calibrations or diagnostic tests within the machine's main menu. Very simple operation, take about 5 minutes, and highly recommended you do that on a daily basis.
Okay, that is nice. Yeah, we will be sending out the slides after we are done with this. We have another question coming in, basically asking us, do we need to adjust the heater for the 16 fiber splicing? Is there any settings to adjust the heater?
I'm assuming you're talking about, we got two issues. If you're talking about the hot jacket stripper, then you don't really have to exchange the heating profile. It still would probably be, if it's a rollable ribbon, set at a level of 4. If you're talking about the splice protector sleeve, you could use your standard FP5 setup, and that would use just your 12 fiber splice protector sleeve would work for 200 micron 16 fiber splice. It's a tight fit, but it will accommodate it and it will work. So no changes to your tube heater.
Okay, nice. I would say cleaning would be number one when you're maintaining a splicer, right? Cleaning. That is something we always need to take care of our machine, and it takes care of the project and us.
Mega, you're 100% correct. With mass fusion splicing in particular, I used to do a lot of field maintenance, troubleshooting, and within 5 minutes arriving on site, I would ask the technician, hey man, can I get my hands on a Q-tip? If he couldn't give me a Q-tip in less than 15 seconds, we were going to be working on hygiene in some form. Q-tips, a high reagent grade alcohol or good quality cleaning fluid is a must. I would concentrate on any of those elements that contact the cladding of the fiber after it's been stripped. So you clean that fiber, you get it squeaky clean. The first thing that you have to worry about is your fiber optic cleaver. It has 6 elements that come in contact with that cladding: the elastomer pads, which are 4, the blade itself, and the anvil. And secondary to that, the fusion splicer, believe it or not, there's only 2 elements in a fusion splicer that contact that cladding. It's the V grooves and the V groove chip clamp. Simple swab out with a Q-tip and, again, reagent grade alcohol, and a 2-inch paintbrush you can pick up at your hardware store. are the cleaning tools I use on site for the most part.
Okay, perfect. So is there any particular number of count, or when do we need to clean our V groups? What is the process for cleaning the V groups?
That's an interesting question, and honestly, it's the environment you're splicing in. If I'm sitting here in the studio, I may find myself cleaning that machine maybe once every 3 or 4 hours. But if I'm in a outside plant environment, a hyperscale, if I'm at side of the road on a set of sawhorses with an 18-wheeler going by, I find myself cleaning that cleaver every other splice. So it's really kind of that environment and judging the condition of your splice. Pay attention to your axle offsets. As long as they stay low across the board and they're consistently low, you're doing well. If you notice those axle offsets start to drift up, it certainly would be a good time to clean those elements that we talked about.
Interesting. Yeah. Hygiene, clean, that is something important. And let me take this question. So someone is asking, while heating, basically putting the sleeve in there and you're splicing and heating it, there is an occurrence where the fibers are breaking inside. So I would assume we did that study, and we can concur that if you use any low quality sleeves, there is a higher chance the heating goes from side to the center, basically bringing you an air gap in the middle of the sleeve, and that can break the sleeve, the fiber. So we recommend using the FP05, our sleeves, because those are tested for a particular reason, and those basically heat up accurately and push out the air.
That's an interesting question. The only thing I can say about that, the Fujikura FP5 sleeves for 12 fiber and 16 fiber 200 micron have been tested, thermal cycled through the various environmental conditions that they're used under, and they've passed. All sleeves are not created equal. They do use different plastic, different paraffins, different hot glue melts, so they may be some variable there you have to be aware of. But also, I would say if you're breaking a lot of splices during the transition from the splicer to the getting the tube heater on and getting the splice protector sleeve in the tube heater, I would pay attention to my tension. I always tell folks, tension's my friend. Don't be afraid to pull the fibers. They're going to be pretty strong on the tension side. If they're not and they're breaking, if you're pulling the fibers ever so slightly, then you would want to do something either with your hot jacket stripper, the cleaning fluid, because a lot of times it doesn't break at the splice. It will be to the left or right, where the mechanical apparatus used to strip and clean could be creating some pretty significant surface flaws.
Interesting. And and for the splice sleeve, I guess we can still use the FP05, which is used for the 12 fiber too, right?
That's correct. When I said 16 fiber count, you can use the FP05 sleeve. You can, but it is 200 micron coated fiber. If you happen to have a 250 micron 12 fiber and using the 250 micron 16 fiber V grooves, you would have to use a larger sleeve in that particular scenario.
Okay, understood.
But for the hyperscale world, 200 micron, 16 fiber, the FP5 sleeve will work.
Yeah, okay. And there was a question basically asking us about splicing, actually active splicing. So I would say please go back to our third webinar where we actually showed how to splice, and the splicing procedure is exactly same as the 12 fibers. So that is the reason I'm guessing we are not really showing the actual splicing procedure today. And can you give a detailed instruction? Do you know the color coding of the 16 fiber? Because there is a lot of different colors right now, and there is confusion. And I guess
I understand your heartache with that, and I can tell you that Fujikura uses. They must have had a Japanese engineer go down to Charleston, South Carolina, and start using a lot of the mauves because they're very unusual colors that I probably would give you the wrong name of them. I can certainly send you a photograph of the color code for the various ribbons out there, but I do not know if there's an ITU spec or a standard for the 16 fiber sequential ribbon array. I have to find that out and come back to you, which
Okay.
I'll try to do.
And does our CD30 also support the 16 fiber similar to CD50?
I'm not sure. The CT30 fiber width is a little bit narrower as far as the pad distance. So I would be reluctant to say that it would be a useful tool for 16 fiber. I can tell you that, we're constantly developing products, and we're very excited to move forward with some new developments. Hopefully we'll have those out in the industry in the near future. But that being said, that would be one of them. How do we improve our capabilities with 16 fiber across the board? I can tell you that your input in the field, the folks that use this stuff on a daily basis, is paramount. What you like, what you dislike, what you would like to see the improvement. I know I've heard comments. You mentioned the CT30. I've heard the CT30 cleaver. They like that because it's small and compact and can be operated with one hand. We hear those messages, and we're certainly adding that to our recommendations to Fujikura, our parent company, as they develop these new products. And I think we're going to be excited with what they developed.
That is correct. Yes. And just to note, CD30 is a discontinued product. So I would highly encourage people who are using CD30 to upgrade to CD50 so that you basically have all the features covered in there.
Any more questions, Mega? I think we're finished with the question and answer session. I will say that, hopefully this is going to be a two-way street. AFL, we've been in this business for going on 40 years. We feel like we know what we're doing, and we want to assist you guys to be as productive as possible. With this hyperscale industry, there's always a new development on a daily basis, and we want to hear from you. What you like, what you don't like, what you'd like to see, how we can improve. We're always willing to do that.
Yeah, for sure. And I also wanted to add, please reach out to your local sales managers or AFL sales team or your distributors for the 16 fiber products, because I've seen a lot of questions basically asking about the part numbers. You can also find the part numbers in our AFLglobal.com. You have all the products in there, and if you hover over the 90R spec sheet, there is a lot of different accessories tab, and you can find the 16 fiber accessories in there.
And I will mention that the AFL Global website, there's lots of resources, a lot of videos, illustrations, PowerPoints, all that stuff is accessible to you. And if there's something that you don't see that you need information on, don't be afraid to reach out to the team, and we certainly will try to get you the answers.
Awesome.
Thank you very much for your time. Charlie, I'm going to let you take over from here.
Great. Thanks, Mega. Thanks, Craig. So a few people did ask about the slides, and they are available to download now in the app. So there is an attachment icon on the right side of the control panel. It's up right next to where the question mark is for asking a question, and you can download a PDF.
I'll take over. It sounds like Charlie may have dropped.
No, he's in.
Can you not hear me?
I can hear you,
can
Charlie.
hear you
I
now.
apologize. Mega had me on that. I apologize.
Yeah, the slides are available right now. There's an attachment icon in the upper right side of the control panel, and you can download them there. Just want to remind everyone of some key contacts that we have up on the screen here. So Mega and Craig's contact information is here in case you have any questions that come up after this webinar. And also the Splicer technical support information is listed here too, with the key contacts if you need to reach somebody there. And on the last slide, we provided some quick links to some key Splicer web pages you may be interested in. This slide is in the handout, in the PDF. It's hyperlinked, so just click on any of those titles there, and it'll open up the page in your web browser. So thanks again, Megan, especially Craig, for the presentation. Thanks everyone here for joining in and your questions today. We had a large number of them come in. We'll get back to you on any that were not answered here today. A survey will be sent out after the webinar. We appreciate all of your comments on this one and future webinars. And a link will also be sent tomorrow to the recording for viewing of the webinar. So this concludes our webinar for today. We hope you all have a good afternoon and good evening. Thank you very much. Thanks again.